everyone for coming. For the people who are here the first time, we are SIOS, Student Initiative for Open Science. We formed quite newly, and we are trying to promote the open science ideas and practices among the student community. This is our third lecture about the inconvenient truth of the p-value. Just before we get started, very quickly, today there's another open science event at 4 around the corner in SO2 about data management, and students also get a colloquium pound. So if you want to make an open science afternoon, you should definitely go there. And also in 2 weeks we have our last event of the year. It's a panel discussion where PhDs from different departments discuss how they apply open science in their specific fields. So please all come there and bring your friends. And now I would like to give the floor to EJ Wagenmaker about the talk about the PA. Thank you.
Great, thank you very much. So I'm happy to be here, and as I prepared the talk, I realized that it was a long time since I said anything really negative about a p-value. And I also discovered that I really intensely dislike p-values, still. And in addition, I discovered that if I wanted to say everything negative about a p-value, then an hour isn't enough. So I'm only going to give you the tip of the iceberg complaints on my part. And of course, the inconvenience about the truth, which in my opinion is that p-values don't really serve the purpose you would like them to serve, is that 99.9% of empirical sciences depend on the p-value for their conclusion. And sometimes I discuss p-values with people on Twitter, for instance, and then renowned psychologists will say, oh, I think the p-value is just fine. And I wonder, what makes you think it's just fine? I'm pretty sure that if we had a discussion about it, I could quickly convince you that it's not fine. So why do people say it's fine? I think because they fear the consequence of admitting that it's not fine. Because now you need to do something else. And what then should you do? So in my early years, I just critiqued the p-value. But at some point, a friend of mine, Mark Stivers, told me, that's really not good enough, you should provide people with an alternative. So that's what I'm going to do in this talk as well. So I'll first spend some time arguing why p-values are bad. Then I'll show you why the alternative, Bayesian inference, is good. And finally, I'll show you how you can obtain Bayesian benefits by using JASP. That's the free and open source software package that we're developing here at the University of Amsterdam. Oh, and by the way, this is completely informal, so if you don't understand a certain thing, or you want to discuss something, or you have questions for clarification, just raise your hand. So we're first going to focus on why p-values are bad. And like I said, I don't have time to delve into the details, but I just want to give you an idea of the various arguments that exist in the literature. The ones that I like. The arguments that I like. Oh! Before we start, of course, we have to start with the question, what is a p-value? So I came poorly prepared. As I was thinking about this lecture, I thought I should do what I do when I teach this topic to second-year students. I should have money on me and then offer people €5 for a correct definition of the p-value. And I've done this before. Sometimes I get to keep the money. Usually I have to give it away, but only after several attempts. So let's see if somebody... so I don't have any money to offer. I do have money to offer, but it's 50 guilders, and I think that's too much to answer this question, right? Because you should all know this, of course, right? And I don't think... so most of you are students. I don't think we'll get better answers if the room was filled with full professors. This is just a general blind spot that people have. But, you know, you're well trained in methods, so who would like to give it a shot? What is the p-value? Can I have a definition? Okay, I'll start. The probability that.
The probability that we obtain a parameter this or more extreme under if the null hypothesis is true?
Yeah, so that's very, very close. What do you mean with the parameter?
Like a parameter of, oh, okay. Not a parameter,
Well, but it was
like,
close.
like a t-value or
Well, not a p-value.
not a t.
A t-value, right, a summary statistic. Yeah. So, good enough. So, it is the probability of obtaining the value of a test statistic, a summary of your data, as extreme or more extreme than the ones you found if the null hypothesis is true. So, the usual mistake that people make is they do say that it is something that you expect if the null hypothesis is true, but they forget the fact that it's not just the probability of the observed data, but the probability of data observed or more extreme. Right? So when you think of a picture where you have the bell-shaped curve, the p-value is an integral, a tail area integral. So it's not just the data you observed, it's also the more extreme cases. Okay. So that's the definition, and here are some problems with the p-value. Now, of course, the p-value in itself is just a number, and you can hardly blame it for anything. It's how people use it that is the problem. So, one limitation of it, and this is the point that I will stress, is that it does not depend on what the alternative hypothesis predicts. Right? From the definition you just heard, it is what you expect given that the null hypothesis is true. But what if the alternative hypothesis is true? What do you predict then? So if you think of the p-value as a measure of surprise, if the null hypothesis is true, what if the data are just as surprising if the alternative hypothesis is true? Would you then feel comfortable rejecting the null hypothesis in favor of the alternative? You probably wouldn't. Another issue with the p-value is that it depends on those data that were more extreme. Right? Not just the data you observed, but also the data sets that you could have observed that yielded more extreme outcomes. And this probability for those data that you never saw, they depend on the intention with which the data were collected. To give you a very simple example, let's say I throw a coin and I find the first time I toss it, it's tails, 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 heads. And based on now I want to do a hypothesis test, is this a fair coin? Now, we have to look at the probability of these data under the null hypothesis or more extreme data. Right? So a data set that's more extreme here, so this one counts, but the one that's more extreme is where you have all tails. So these are the probability of these two data sets are relevant if you want to compute your one-sided p-value. However, implicitly here, we have assumed that the experimenter intended to toss the coin 6 times and then stop. But what if the experimenter was actually planning to throw the coin until the first heads? Right? That data set could have been obtained, but now this is not a more extreme case. In fact, this data set is impossible under that scenario. Under that scenario, a more extreme data set would be tails, 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 and then heads. This is a more extreme data set. So now this one counts towards the p-value. So you now get different p-values for those two cases, even though the data are identical. Some people find this problematic. P-values do not offer a coherent framework for updating knowledge or quantifying evidence. So if you've done an experiment and you found a particular p-value and now you do an exact copy of that experiment in exactly the same population, right? There is no way to say take that p-value and somehow incorporate it into the analysis of your second experiment. Whereas I'll show you later on that with in the Bayesian paradigm, you can just continue to analyze data as they come in and simply update your your knowledge on a continuous basis. Some more problems. This is one of the most famous ones. P-values do not allow you to quantify evidence in favor of the null hypothesis. Right? So you do an experiment and you find that your p-value is 0.25. What do you conclude? Right? It could be that the data actually support the null hypothesis so that there is evidence for the absence of the effect. But it could also be that you were just terribly underpowered, which means that there's absence of evidence and the data are uninformative. We've already gone over the fact that monitoring evidence as the data accumulates is problematic with p-values. You can do it, but it requires all sorts of assumptions and corrections, and those have their own problems. The final one is actually a problem with statistics in general, I think, to be fair. So there is a clear tendency, and I'll show you a concrete example later on, to say that if that p-value is below 0.05, the usual threshold, to say that we have found the effect. And if it's bigger than 0.05, you say we did not find the effect. There's no evidence for the effect. Right? And that is kind of all or none thinking. It's also called sometimes the cliff effect, where everything smaller than 0.05 is true and everything higher than 0.05 is false. But in reality, of course, we can often be simply unsure. Why do we need to feel forced to make an all or none, yes or no decision? Maybe you just want to see more evidence before you commit to a decision. So this is a good example. This is a famous statistician, Larry Wasserman, and he commented on the statistical analyses concerning the discovery of the Higgs boson. So he said, Forbes magazine reports that it cost about $13 billion to find the Higgs. For that price, we deserve a definite answer. And he meant the p-value. And so when I find this weird that a famous statistician would say something like this, because clearly this has nothing to do with deserve. Right? You have the data, and the data give you evidence, and if it's inconclusive, it's inconclusive. So I think that for the price of $13 billion, people would like not to be misled, which means that we shouldn't sweep uncertainty under the rug. And that sentiment is echoed by another famous statistician, John Tukey, who said that statistical procedures should not be used for sanctification, for the preservation of conclusions from all criticism, for the granting of an imprimatur. So, and this is often how p-values are used. So at some point here at the University of Amsterdam, a student came up to me and said, I did an experiment to figure out whether people can guess who's calling them. Right? So sometimes people report this, the phone rings and they think, oh, this is going to be my grandmother, and they pick it up and it's their grandmother. So you can study this experimentally. You have to control, of course, for all kinds of factors. And she had found the effect because that p-value was smaller than 0.05. So I said, I don't believe it. And then she was upset at me because I wasn't playing by the rules. Because the rules say it's smaller than 0.05, now you should believe it. And I think that's a very bad use of p-value. So here I'll show you one concrete example that really focuses on the first problem, that p-values do not depend on what the alternative hypothesis predicts. They only look at what the null hypothesis predicts. So let's see what that will do. So I'll discuss the case of Sally Clark. Who has heard of the case of Sally Clark? It was a famous case years ago. So Sally Clark had 2 children die of cot death, a sudden infant death syndrome, bigedood in Dutch. So the chance of that happening, that your 2 children die of cot death, is really low. If you believe these deaths are independent, that's a big assumption, but if you believe that they're independent, you get to a probability as small as 1 in 73 million. Right? So the null hypothesis is that Sally Clark is innocent, and now we find this really, really unlikely event. Can we now reject the null hypothesis and send her to jail? Because this is what you do if you believe in p-value logic. Well, the expert for the prosecution, Professor Meadow, argued that that would be a good idea. Actually, that's not quite true. He was a little unsure for 2, but for 3, definitely. So he attributed many unexplained cases of cot death to a disorder known as Munchausen syndrome by proxy. So from Wikipedia, according to that diagnosis, some parents, especially mothers, harm or even kill their children as a means of calling attention to themselves. And there's something like Meadow's law that says 1 cot death is a tragedy, 2 cot deaths is suspicious, and until the contrary is proved, 3 cot deaths is murder. So in 1999, Sally Clark was convicted of murdering both babies and sent to jail. And of course, like I stressed before, there's a similarity here with null hypothesis significance testing. Right? A very rare event occurred, very surprising, given that she would be innocent. So therefore, she's guilty and sent her to jail. Is that okay? Well, it's not okay. Why is it not okay?
If we took the standard p-value of 0.05, then we should actually send all mothers of 6 babies.
Yes, yes, that's a very good observation. Yeah. So, so you could say maybe if you know this, maybe you set that p-value a little lower, just so low to be able to send Sally Clark to jail. But yeah, no, that's a good point. Basically, unlikely things still happen quite a lot, right? So even if it's a very small chance, it does mean, right, if the chance is 1 in every 10,000, right, that does mean that 1 in every 10,000 you can send to jail, which is not what we want to do. So yeah, that's a good point. There's another point that is important here.
You automatically assume there's only one other hypothesis, so that's the black and white thinking also. So if the null hypothesis is not true, the alternative hypothesis must be true.
Yes, that is true, but in this, so you're saying that in this case we could have SIDS, or she's innocent. The alternative is murder, right?
Yeah, but
maybe there's another hypothesis that could be entertained. That's true.
In Bayesian way, you would also look at the probability of killing your both of your child.
Yes, exactly. That's exactly the point. So it may be very unlikely to have 3 children that all die of cot death. Right? But it's also very unlikely to have a mother kill her 3 children. So if you want to know whether 3 deaths is evidence for murder, you have to compare the probability that they've died of SIDS to the probability that they would die from murder. Right? Murder is actually more rare than cot death. So we've had that, and so the president of the Royal Statistical Society in England sent a letter disputing this case, and this is what's in the letter. The jury needs to weigh up 2 competing explanations for the baby's death, SIDS or murder. The fact that 2 deaths by SIDS is quite unlikely is taken alone of little value. 2 deaths by murder may well be even more unlikely. What matters is the relative likelihood of the death under each explanation, not just how unlikely they were under any one explanation. Okay? So I hope that at this point you think like, the president of the Royal Statistical Society makes a good point here. Right? This was statistically wrong what happened in this case. But now back to our p-value. That p-value only considers how rare the observed data are under the null hypothesis. It ignores the fact that those observed data could be just as rare under the alternative hypothesis, or perhaps even more rare. So the p-value logic has the same flaw as the logic that was applied to send Sally Clark to jail. So here I adjusted the letter for Peter Green just a little bit to make it statistically appropriate for the p-value debate. Researchers need to weigh up two competing explanations for the data: the null hypothesis or the alternative hypothesis. The fact that data are quite unlikely under the null hypothesis, that's the p-value, is taken alone of little value. The data may well be even more unlikely under the alternative hypothesis. What matters is the relative likelihood of the data under each model, not just how unlikely they are under one model. And here, of course, the inconvenience of the story already makes its appearance, right? It's easy to look at the Sally Clark case and say, like, oh, this is a statistical blunder, that's really dumb, you should take both of those things into account. And then when you present this open letter to people, right, they're much less likely to say, oh yeah, reporting p-values is really dumb, we really shouldn't do that. And that's because of the alternative and the unpleasant prospect of having to learn a completely new way of doing things, in my opinion. So there's one more problem that I want to discuss with you, because it's a famous saying, and it actually took me a while to understand it, and it's kind of funny. It's one of the best definitions of p-values that I know, but it's a little complicated, and that's only right because the p-value concept itself is really complicated. I mean, the correct definition was immediately given here in this audience. But if you go tell your grandmother what you did, and she asks you what is the evidence, and then you come up with the definition of a p-value, that won't go over so well. Okay, so that other problem that I want to discuss is that p-value depends on data more extreme. Right? So it's not really, p-value is not the probability of the observed data under the null hypothesis, but it's really the probability of those data plus the stuff that's more extreme, that you actually never observed. So Harold Jeffries, one of my Bayesian heroes, has had this to say about p-values. What the use of the p-value implies, therefore, is that, here it goes, a hypothesis that may be true may be rejected because it has not predicted observable results that have not occurred. This seems a remarkable procedure. So I'm breaking this down for you because it's very difficult to absorb this at once. So he says, okay, a hypothesis that may be true, that's the null hypothesis. It is rejected because p is smaller than 0.05. And why is it rejected? Because the probability of results more extreme than the one you actually found is low. And so this is a more philosophical objection, but it does have practical ramifications that we will get to later. Okay, so this was the first part about p-values. So now I have a few slides on Bayesian inference. I don't have time to delve into the details and give you a complete overview of all the concepts in Bayesian inference. So I'm going to keep this really short, stick to the basics, and then present to you a series of examples. And hopefully those examples will be more entertaining and informative than an abstract exposition. So this is really what Bayesian inference is all about. So we have a cycle here. It's a cycle of learning. So we start on top with prior knowledge. From our prior knowledge, we can make a prediction. Then we observe data, and we get a conflict between what we predicted and what the data actually show. And that conflict is a prediction error. And that prediction error drives a knowledge update. And after your knowledge has been updated, you then have posterior knowledge, and that forms the basis of a new cycle. And so you just continue to learn as you see more observations. And this is remarkably similar to the empirical cycle, that is a conceptualization of how scientists learn. And it's also very similar to reinforcement learning. For instance, I don't know if you came across this, but certain learning algorithms are now able to play chess and Go really, really, really well. And they do this because they just played millions of games against themselves. And they just learn from playing against themselves, and they become really, really good. And it's basically, conceptually, it's because of this mechanism. Right? If they lose a few games playing a particular move or maneuver, they learn that that's not the right thing to do, and they change their knowledge and they don't make that mistake again. So I think this is this is not the only equation. Okay. But it's very conceptual. So we start with our prior beliefs. Theta is the unknown. It could be a hypothesis, or it could be the parameter of a model. But we have prior beliefs about something that we don't know. And after we see the data, we end up with posterior beliefs. So the relative plausibility of the values of this unknown quantity after we see the data. And the change from our prior beliefs to our posterior beliefs, so what we have learned from the data, that is given by this predictive updating factor. So it simply says that if a particular value of theta predicts the data relatively well, it will increase in plausibility. And if it predicts the data relatively poorly, it decreases in credibility. And this process of increasing and decreasing in credibility, according to predictive success, that's conceptually identical to what I just showed you with the learning cycle. So this is just putting numbers on that cartoon that I showed you before. Okay, so let's go to some concrete examples. There's a serious one and there's a not so serious one. But they all make some key points, and we'll, I hope to get to most of the main talking points. So, the first example is, it was published in May, and it deals with progesterone, and its possible helpful effects in preventing a miscarriage. So this is a pretty serious topic. The second example deals with the question whether movies with Adam Sandler are profitable regardless of their quality. And that's less serious, but it still has there's some important lessons here. Okay, so I'll do these analyses in JASP. I have the slides with the results on them as well, but I think it's more fun if you just see me do the analyses in JASP. Also because I hope to impress upon you the ease with which you can do this. So that it's not so difficult to abandon your beloved p-value and embrace something else. Right. So JASP presents both classical analyses. This is Ronald Fisher, who was one of the people who really promoted p-values, and Bayesian inference. So there's something in here for everybody, and there's a large team of people, some of whom are in the audience, who work on JASP. It's also something that we do together with students who volunteer to work with us. So if you're interested in contributing to JASP, just send me an email. So this is the article. A randomized trial of progesterone in women with bleeding in early pregnancy. So there's a lot of text here. You don't need to read it, but I am going to read to you the key parts so you understand the importance of this problem, right? Because sometimes you can think, oh, statistics, it's so boring, it doesn't have consequences. Well, we have had an example of Sally Clark here. For her, it had consequences. And you will see that in this trial, there's also consequences. So, bleeding in early pregnancy is strongly associated with pregnancy loss. Progesterone is essential for the maintenance of pregnancy. So there's some early evidence that it actually helps it helps prevent women from losing their child. So the early evidence was kind of weak, as small studies. So these people took it seriously. They did a multi-center, double-blind, placebo-controlled trial. And the primary outcome was the birth of a live-born baby after at least 34 weeks. So here are the results. So you can see that they actually tested over 4,000 women in this experiment. And they reported 75% live births in the progesterone group and 72% in the placebo group. 3% effect. But the p-value is 0.08. So what do they conclude? The incidence of adverse events did not differ significantly between the groups. And that's true, of course. But is that the only conclusion that we can draw from these data? This seems like a very impoverished conclusion. And perhaps this conclusion will lead you to think that progesterone is ineffective. That we now know that it's ineffective. But with a value of p-value of 0.08 and a difference of 3%, you may wonder maybe there's something more that could be said about this. And in fact, something more was said about this. So here's to drive home the point that the authors made this conclusion. In the conclusion section, it says the drug did not result in a significantly higher incidence of live births than placebo. Right? So if you're a doctor and you want to prescribe a treatment and you read this literature and you just read the conclusion section, you would say, I'm not going to do anything. Okay. So I'll show you later why I think this is unwise. But I'm not the only one who thinks it's unwise, because here is the author of the actual paper. And as you will see, the author of the actual paper believes that it does actually help, even though he wasn't allowed to say this in the paper. So he says the p-value of 0.08 didn't cross the magical bright line, but it wasn't far from it for those who seek reassurance in a p-value. So he says we are left with only some statistical uncertainty, but scientific inference is much more than statistical inference. What is the context? What is the biological rationale? Is there any supportive subgroup behavior? What is the external evidence, etc.? And then, so this is a tweet thread of about 30 messages. And then he goes over all the reasons why he thinks that there is an effect. Right? And I don't have time to go into this, but I'll just show you there's a biological rationale. So this drug is vital to support pregnancy. If you remove it, you will certainly get a miscarriage, etc. So there's a biological gradient, there's external evidence, this is a meta-analysis. I don't have time to go into this, but he has a lot of arguments for why this drug actually helps. In fact, he concludes, we judge progesterone to have a probable effect in women with early pregnancy bleeding. And then he says, we believe the evidence has policy implications. So here we have a paper in the New England Journal of Medicine, right, one of the most prestigious medical papers, where the conclusion is there's no significant effect. And then a few days later, the author says on Twitter, this should have policy implications. It's a little strange, perhaps. So we are now going to do a Bayesian reanalysis of these data. So these are the exact numbers. So you see that with progesterone, those are the numbers, and with placebo, you have those other numbers, but I do want to call your attention to the fact that the difference is actually 2.2% and not 3%. Right? That's because of the rounding that they did in the paper. So it's actually 2.2%, so it already looks a little bit less compelling, perhaps. But what we want to ask now, we want to go beyond this p-value and ask how much evidence do the data provide for the hypothesis that this drug helps? So what is evidence? Well, evidence, according to a book written by Evans, I will show you the book later, it's a great book. Evidence is what causes beliefs to change. And so evidence is measured by change in belief. It's almost a tautology. But from a Bayesian point of view, this is essential, right? Evidence is what causes beliefs to change. If you are in a court case and the prosecution presents evidence that the defendant is guilty, right, it would be very strange evidence if after looking at it you thought, oh, the defendant is probably not guilty. Right? That's not what evidence is. Evidence is the thing that, in this particular case of the prosecution, makes you think that it's more plausible that the defendant is guilty than before. So this is that book, Michael Evans, Measuring Statistical Evidence Using Relative Belief. Wonderful book, highly recommended. So here's our Bayesian reanalysis. So I'm not going to go over the details of what we did. The only thing that's relevant is the following. I'll just try to explain it conceptually. So we have a particular rate of births in the placebo condition, and another rate of births in the progesterone condition. In our statistical model, we have two parameters. That's the mean of the two and the difference between the two. And so the important parameter for testing whether it has an effect or not is that difference parameter. In this case, that's the parameter psi. So if psi is 0, the two groups are identical and there is no difference between them. That's the null hypothesis. If psi is something else, then there is a difference. So in our Bayesian framework, the null hypothesis stipulates that psi equals 0. The alternative hypothesis stipulates that it's something non-zero. Right? But what is it? Well, when we're Bayesians, we need to acknowledge that we're uncertain about the true value and put a prior distribution on it, where we acknowledge that it could have all kinds of different values, but some are more plausible than others. So let me actually, before I go to JASP, this method was proposed earlier by Cass and Vaidyanathan, and it's implemented in the CRAN package A/B test and also in JASP. And we have a blog post about this A/B test on the blog Bayesian Spectacles. Right? So it's called an A/B test because you're comparing two proportions, and the name is really from industry, where they often look at how effective certain websites are, which one gets more clicks. So the real work here was done by Quentin Gronau. Akash put everything into JASP, and I looked on from a distance. So let me show you how this works in JASP. So this is actually the developer's version, and we hope to have it released on Tuesday. So I'll open the file. So here you see the data, right? It's a 2 by 2 table. We have placebo and progesterone and live births or non-live births. So we immediately, I don't have time to give you a complete run through. I immediately go to our Bayesian A/B test. I'll add the relevant numbers in the relevant boxes. And we immediately get our result. Let me just tick a box so that the result is easier to see. So what we have here is the best model is on top, and the best model says the log odds ratio, the difference between the groups, is 0. So there's actually support for the null hypothesis. But this support is pretty weak, because the next best model says there is a positive log odds ratio. The drug helps. It's not as good as the null hypothesis, but it's out-predicted only by a factor of 2. So that means that if you start out with a 50% belief that it's 0 or positive, after seeing the data, you now have a 66% belief. So that still leaves 33% for you being wrong. Right? So it's completely not compelling. However, you can do another analysis. So actually, before I do that, I'll show you a plot of the prior and posterior distribution for that key parameter that indicates the difference between the groups. You see the dotted line here is our prior distribution, and the solid line here is our posterior distribution. So it's clear that from the data we actually learned a lot, because our posterior distribution is very peaked. You can also see that most of the posterior distribution is to the right of 0. So if there is an effect, it's much more likely to be positive than negative. So with the same data, you can test different hypotheses. We have seen that if you test the hypothesis, it's absent, 0, versus positive, that only gives you a so-called base factor of 2. The null hypothesis outpredicts the hypothesis that it's positive only by a factor of 2. But what we can also do is compare the hypothesis that is positive versus negative. Right? This is a very different question, but we can easily do it in the program. We go to advanced options, and we just assign 0 to the prior probability that the effect is absent. And what we get then is a base factor of about 18. So the data are 18 times better predicted by the hypothesis that it helps instead of hurts. So I have to move on in the interest of time. So the data are about 18 times more likely on the hypothesis that it helps rather than hurts. But that was never the question. That was never the reason for setting up the experiment. People already knew this. What they wanted to show was that it outperforms placebo. Right? So that it's actually helpful rather than absent to convince the skeptics who would argue this doesn't do anything. And if you do that analysis, you see that the evidence in favor of the null hypothesis is very weak. So this is what Harold Jeffries called not worth more than a bare mention. And so here we did an analysis where we looked at all kinds of different prior distributions for that parameter that governs the size of the difference. And this plot is actually not important. The only thing that's important here is the legend. Because the legend only goes from 1/2 to 2.5. The entire range here is worth no more than a bare mention. So it doesn't matter how we analyze these data in a Bayesian sense. The result is always the same. The data are not compelling. So even if you were to cherry pick your prior distribution that would give you the most evidence for either of the hypotheses, you wouldn't get much. I'm going to skip this plot. And I just want to go quickly to the second example, right? So this example shows that we actually know more than we did before, because we found this p-value of 0.08. The conclusion was it is not significant, but now we know that the result, even though 4,000 women were tested, we know the result is we have an absence of evidence. We don't have evidence for absence. So in that sense, it's consistent with what the author claimed, although taking these data and arguing that those data actually support your hypothesis that it helps is going a bit too far. Okay, so a brief commercial before we go to our second example. We teach 2 workshops on Bayesian statistics. One is a workshop on Bayesian statistics, really the use for the kind of analyses that I just showed you, t-tests, ANOVAs, etc. And that's August 22nd and 23rd here on this campus. And then the next week, the entire week, August 26th to August 30th, we do our 8th annual workshop on modeling for cognitive science. So that's actually the more original kind of using Bayesian statistics, where you really construct specific models for interesting cases. So not at all like a canned analyses like the t-test. But both are really good. Okay, so I have a second example, but I probably don't have time if we want to have a...
10 minutes?
I will just speak very quickly. That's the way you deal with these situations. Okay. Are movies with Adam Sandler profitable, regardless of their quality? One of my favorite examples, actually. So, why this example is probably something you're wondering. Well, I was looking for an example where the data are given to you by nature, or in this case, Adam Sandler. So, you are not running an experiment. The data collection is not under your control. Right? When we tossed the coin, it was under your control, but when we get data from nature, it's not under your control, and you still want to learn something. In fact, you could argue that learning in the real world is almost always like this. Doing experiments is actually something we haven't been doing for a long time as a human race. So, I was looking for this example, and here it was. South Park episode 166, one of the better ones, where the series protagonist Eric Cartman pretends to be a robot from Japan. The Osmo 4000. Hollywood movie producers kidnap the robot and force it to generate profitable movie ideas. And the robot starts to generate completely off-the-wall, silly movie ideas, and a lot of them, but 800 star Adam Sandler. And so I looked at this and I thought, what are the makers of South Park trying to tell us? And I felt that what they were saying is that movies with Adam Sandler are profitable regardless of their quality. So how do we test this statistically? So we have to be more specific. So I went to the movie review website, Rotten Tomatoes, and looked at all the movies that had Adam Sandler in them, starting at 2000, I believe. And what I looked at is box office success in millions of dollars, and the ratings. So the ratings go from 0, everybody hates it, to 1, everybody loves it. And if more people go to see good movies, you should find a positive correlation between how much the revenue and the ratings. But that's not, that's the South Park people endorse the null hypothesis. Right? They postulate the null hypothesis, that there's no relation. A priori, perhaps unlikely. Well, let's see what the data have to say. So, we go to JASP, and so here are the data in spreadsheet format. So you can see, for instance, let's take an example. So row 12, a movie came out in 2005, 9% fresh, this is not good. 22 million, reasonable, for Deuce Bigelow European Gigolo. 2007, 14% fresh, not very good, but almost 120 million for I Now Pronounce You Chuck and Larry, well, etc. Right? So now we want to do a Bayesian analysis of this correlation. So let's go straight to our correlation. And let's drag in freshness and box office success. And let's tick some boxes. So this is actually also the reason why I prefer to work in JASP myself, even though I'm an R programmer, and JASP is based on R underneath the hood. But you saw me just with a few mouse clicks. I can generate pretty comprehensive Bayesian analysis, and if I had to do it in R, it would take me much longer. So, what do we have here? First, it's always important when you examine a correlation to show the scatter plot. So this is the scatter plot. And you can see from the scatter plot already that, hey, there doesn't look to be a positive correlation. Then what can we conclude about our correlation coefficient? Well, the dotted line gives our prior, which says any value from -1 to 1 is equally likely, and the solid line is our posterior. So what have we learned? We have learned that extreme data, or extreme values of the correlation coefficient, either negative or positive, have become less likely, and values near 0 have become more likely. they predicted better. And if we quantify this with a test, we can say that the data are about 4.5 times more likely under the hypothesis that there's no correlation than under the hypothesis that there is correlation. So this is, very importantly, evidence in favor of the null hypothesis. And not only can we have evidence in favor of a null hypothesis, I ticked the box that said sequential analysis, which means that we can actually track the evidence as Adam Sandler makes more movies. So here we have that plot where I think there's 31 movies in here. So as Adam Sandler makes more movies, we find increasing evidence for an absence of a relationship between movie quality and revenue. And there are frequentist ways of doing such an analysis. And a frequentist, a p-value lover could do this analysis and make some kind of ad hoc assumptions and corrections and stop here and be happy. Until Adam Sandler produces movie number 32. And then there would be a problem. Because now, from a frequentist perspective, suddenly you are required to do another test. But you can't keep doing tests forever because you have a multiple comparisons problem, basically. But what is the right correction? Well, we really have to ask Adam Sandler for his intentions. When will he stop making movies? I don't think he'll stop soon, because the average revenue is 120 million for his movies, and quality doesn't seem to matter at all. So I think he'll keep going. Okay, so let's finish up. So, what can we do with our Bayesian analyses? We can attach probabilities to parameters and hypotheses. We can quantify evidence for any hypothesis we wish to specify. I only looked at the defaults here. I could have made all kinds of interesting changes and looked to see how robust the conclusions were. There's a lot of options in JASP as well. We can monitor the evidential flow as the data come in. And we can assess sensitivity of our conclusions to alternative prior specification. And I particularly, out of all these, I particularly like the monitoring of the evidential flow. I think for a practical researcher, suppose you're doing a study, an fMRI study on autistic children or something, and suppose you already have really good evidence after 20 kids, but the analysis you planned demanded that you test 100. Then you're in the situation where the experiment requires that you continue, right? Wasting everybody's time and money. So that's it. Thank you very much.